So once again, good morning, everyone. I'm delighted to be here today to talk about a fascinating topic that lies at the intersection of data analysis, artificial intelligence, and predictive modeling, which is time series forecasting with machine learning. In today's world, we are overwhelmed with vast amount of data, and many businesses, researchers, and individuals are constantly trying to find a way to extract valuable insight from this vast amount of data. So time series in particular is ubiquitous and found in various domains such as finance, economics, weather forecasting, sales, stock market prediction, energy consumption predictions, among others. In time series, the way time series works is that it captures sequential nature of data where each observation is associated with a specific time. So let us take an example of time series data. For instance, now, if you take an example of stock market price, daily stock market price. So if we look at it, there must be a time, maybe date for each day. This is the price for 1st January, 2nd January, throughout the year. So if you have a record of 1 year or 20 years of historical data of stock market, so you can use that historical data using my supervised machine learning to make an estimation or prediction. Like in economics, they normally call it estimation, but here we call it more of forecasting. So this temporal aspect adds an extra layer of complexity when trying to make prediction or understand the underlying patterns of the data. Because if you take an example of sales in a particular supermarket or mall, normally their sales must include date and time. So in time series data may contain date with some other variables, or date, time, and other variables.
Question, Zaharaddeen. So what is the difference between forecasting and prediction?
Yeah, because I will come to that. I will explain. I will explain later. It's just an introduction. So traditionally, time series forecasting relies on statistical techniques. An expert since the beginning of human civilization, they are trying to use time series forecasting to predict the future event. So machine learning is a branch of AI that focuses on enabling computers or training the AI models by training the AI models, they can explicitly make decisions. So now we are now talking about time series forecasting. As I have said earlier, when we are talking about time series, we are talking about like a transaction that has a time stamp. It may has date and time, or date and time, depending on the type of the data set we have. Now we are now talking about time series forecasting. In the previous lecture, you have taken on machine learning, maybe you have used regression problems. So in that we are making prediction. So what is the main difference between prediction and forecasting? In case of prediction, normally we are training our entire machine learning model to make a prediction on the entire data set. While in case of forecasting, let's say we have our data set, we are using what we call sliding windows or look back, in such a way that, for instance, now I have historical data of stock market price for 3 years. Now from my stock market prediction, from my stock market data set, maybe I want to predict the price, the next price, or the future price. So in case of prediction, normally we are training our machine learning model using regression to measure the prediction error. But in case of forecasting, maybe let's say I want to use sliding window, maybe, let's say 3. I'm using 3 loopbacks so that for each time, I am trying to make a future prediction. My model, but I will train my model, take 1, 2, 3. The first 3 makes the prediction of the next one. Then it will take another set of 3 values and make the prediction of the next one in that order. Assuming that in my data set, I have 2,000 data points. So it will start from the first 1, 2, 3. It will now make a prediction and move to the next 1, 2, 3, and make the next value prediction. Although in time series forecasting, there is normal 1 step forward and there is horizon, whereby you may check, maybe if you specify your look back or sliding window 12, it will now take 12 completely and focus the next 12 data points or values. So now let us look at the introduction to time series. So in this lesson, we will try to learn about time series forecasting, which is very interesting topic. So suppose you maintain an array of smart parking meters that provide data about how often they are used and for how long over time. For instance, now there is a smart parking meters. So you may want to get some insight or valuable information from that data, maybe over the time, because each time a person parks his car, it will now save the timestamp, maybe date, time, and maybe the payment if there is need for that. Accurately predicting when to act as to achieve your goal is challenge that could be tackled by time series forecasting. It won't make folks happy to be charged more in busy time when they are looking for a parking spot, but it will be a sure way to generate revenue to the clean street. So sometimes from that smart parking meters, you can easily generate valuable information. Let's explore some of the types of time series algorithm and start a notebook. So, but before that, let us take at some definitions in time series forecasting that we normally use. First of all, what is time series forecasting? In mathematics, a time series is a series of data points indexed or listed or derived in time order. Mostly, a time series is a sequence taken at successively equally spaced points in time. An example of time series is the daily closing value of Dow Jones Industrial Average, which is a stock market. The use of time series plot and statistical modeling is frequently encountered in signal processing, weather forecasting, earthquake prediction, and other fields where events occur and data points can be plotted over time. So now what is time series analysis? Time series analysis is the analysis of the above mentioned time series data. Time series data can take distinct forms, including interrupted time series, which detects pattern in a time series. There may be a situation whereby you may have a time series data, but it may have a distinct forms. It may have a distinct forms. For instance, now, if you take an example of weather, let's take an example of Kano. Over a year, the pattern of our weather is totally different. You may have like during Harmattan, whereby the temperature is very low. During the dry season, the temperature is very high. It may even reach up to 37, 38, while during the Harmattan, it may be, the maximum may be around 20. And during the rainy season, the temperature will also be very low. So if we look at the way, so making a prediction using that data set, it requires a lot of effort for you to make a good prediction from that data set. So the analysis performed uses variety of methods, including frequency domain and time domain, linear and non-linear, and many more. So like if you go back to math, just like in mathematics, there may be a frequency domain and time domain. There may be a situation whereby our main concern is to forecast the frequency. Our main concern is not time. And in many cases, in time series data, we are not using the date and time. Mostly we are using it as an index. But we are trying to maintain the pattern because our data set, it is in form of it in each row or each data points, it contains date and time. So that is why in most of our time series forecasting modeling, we are just using date, time, date, or date and time as an index. Time series forecasting is the use of model to predict future values based on patterns displayed by previously gathered data, that is historical data, as it occurs in the past. While it is possible to use regression models to explore time series data with the indices as, for instance, as X value on plots, such data is best analyzed using special types of model. So in time series forecasting, we are using models to make a prediction. For instance, normally time series forecasting is a regression problem because our values are always in continuous form. You know, there is quite difference between in under supervised machine learning, we have classification and regression. So in classification, we are dealing with discrete values. When we have a discrete value where we are trying to just make a prediction, maybe a binary classification or multi-class classification, we are just trying to classify. But in case of regression, the values are in continuous form. So whenever you are dealing with time series data is a regression problem because the values are always in continuous form. So one of the most commonly used time series forecasting model is ARIMA model, which is autoregressive integrated moving average. So in time series, we may use either univariate time series or multivariate time series approach to make our forecast of future values. But in our today's lesson, we will discuss about univariate time series. In univariate time series, you may have, normally we have independent variables and dependent variable in any machine learning problem. We have dependent variable and independent variable. That is, dependent variable is the target, while independent variable or variables are the features. So in univariate time series analysis or time series forecasting, you can use, maybe for instance, like in this case, we have CO2, carbon dioxide, which is the only variable we have, while year, month, and month, they are what? They are all timestamps. So if you look at it, we have only one variable. In this regard, if we want to make a prediction, if you want to make forecasting using time series forecasting model like ARIMA, what we will do is to try to divide this column. Some part of this column will be part of our training set, and the other part will be part of our test set. Unlike in the previous problem where in the previous machine learning problems, where when you are using a regression problem, you must have features and you must also have a target. In this case, in univariate time series forecasting, you may have from the same column or from the same variable, you may split it into train and test, because what our main aim is to forecast the future values, is to make a prediction of future values. So we may also have a multivariate time series, which is an advanced one. So I will not talk about multivariate time series forecasting using AI. We will now focus more on invariant time series. So if you look at this data, if you look at this table, the data set consists of 4 columns, as I have mentioned earlier: carbon dioxide, year, month, year, and month. So all these three, apart from carbon dioxide, the remaining 3 features has no influence on our data set. So how can we make a forecast while we have carbon dioxide as our variable? So in time series, you can just split the data set into training and test, or even training, test, and validation using the same column, which is okay. So there are many characteristics of time series, because the way we have our time series data, they differ. Normally, for us to use a good time series forecasting, our data must be a stationary data. It must be a stationary data. But in some cases, you may have a data which has a trend, seasonality. You may have some outliers. You may have long-run cycle or constant variance. Let us discuss these features of time series data one by one. So when looking at time series data, you might notice that it has certain characteristics that you need to take into account and mitigate to better understand its pattern. If you consider time series data as potentially providing a signal that you want to analyze, these characteristics can be thought as noise. We often need to reduce this. Normally, if you could remember from your previous machine learning class, one of the factors that normally affect some machine learning algorithms is noise, because some models, they are sensitive to noise, while some models are not sensitive, depending on the types of data you have. Because some data, normally for a real data, sometimes they contain noise, they may contain outliers. And if not, we are talking about real data, not synthetic data that you have, that you may use, which you may not encounter all these issues. So you may have some noise. So like if you take an example of trends are defined as measurable increases and decreases over time. If you look at the way, if you look at the way time series forecasting data features are, sometimes a time series forecasting data may has a trends or seasonality. Seasonality is defined as periodic fluctuations. As such, holiday rushes that may affect sales. For example, take a look at how different types of food. Okay. Now let us take a look at houses. Let me share. Can you see my browser?
Yes.
You can see my browser.
Yes, sir.
So look at this two. Look at this plot. Look at the way the pattern of this. Look at the pattern of this data from 1955 to 1995. That is 10 years. Look at the way it is decreasing and increasing. Look at. So look at this, the pattern of this, the pattern of this. It was represented using different. This is box plot. So if you look at this, if you look at the way the pattern of the data is seasonal, is seasonality, is seasonal. So if your data set is seasonal, then you may still have some issues while making time series forecasting. All what we want is to have a stationary data, which is very difficult, to be honest. Getting a stationary, sometimes you have to employ some other techniques to decompose that seasonality from your data set, because it's for a real data set, you must definitely have some noise. The data set in most cases is not seasonal. So, but there are some techniques that are provided that you can decompose that seasonality and make your time series forecasting, which we may look at it later. There are outliers. Outliers are far away from the standard data variance. So in your data, in time series data, you may have an outliers. Let me give an example of maybe outliers if we can understand it much this way. Assuming that there are lists of annual income of Nigerians. If you look at the annual incomes of Nigerians or people living in Kano State alone, if you look at it, some on daily basis or monthly, they are not earning more than 30,000, while others, they are earning hundreds of millions in a month. So if your data sets contain this type of data points, how can you make a good prediction of, maybe you want to make a forecasting time series of forecasting of the daily earning income of people of Kano for the next 10 days or the next 20 days. I mean, the next 10 months or the next 20 months using that data set. Is it possible? Because look at it, someone is earning 30,000 and someone is earning millions, maybe 10 millions, or some they are even earning hundreds of millions, maybe some they might even earning it in a month. So that there may be some outliers because it consists of different people from different walk of life. So it will be very difficult for you to make forecasting. So this is an example of outliers. Or let me give you another example. The country I'm now living in is Brunei. Their population is less than 500,000. So if they are in the list of countries in the world, the population of the people in the world, if you look at Brunei, it will just be an outlier. Like Nigeria, we have 200 million plus. Like India, they have 1.4 billion citizens. So, but Brunei, they have less than 1 million people. I mean, less than 500,000. So Brunei will just be an outlier. So you need to employ some mechanism to normalize your data. Maybe you have discussed data normalization in your previous machine learning class. So through data normalization, you can reduce the effect of outliers by maybe using you can use min-max scaling. You can scale your data like using min-max scaling and many other scaling techniques that you can use to normalize your data. There is long-run cycle, independent of seasonality. That data might display a long-run cycle such as economic downturn that lasts longer than a year. If we take an example of COVID-19, so if you take an example of COVID-19, if you look at how it affects the economy, or if you take an example of this last year, in the beginning of Russia-Ukraine war, it has negative impact on the entire world economy. So if you look at the data of many financial institutions, if you look at their data, you will see that downturn must be there. Constant variance. Over a time, some data display constant fluctuation, such as energy usage per day and night. For instance, now, if you have a data set of energy consumption, so that data may have a constant variance because during the daytime, there may be more energy will be consumed because apart from residential areas, industrial areas, they are using a lot of energy for production and many other things. So, and in the night, there may be less depending on the type of the country. For some advanced countries, normally during the day's hours, the energy consumption during the day will be much higher than during the night. So whatever the case may be, in any situation, there must be a constant variance. Either the consumption will be higher during the day and less during the night, and vice versa. And there may be abrupt changes in time series data. The data may display an abrupt change that may need further analysis. This abrupt shortening of business due to COVID-19, for example, it causes changes in data. COVID-19 has affected the entire world economy. So if you look at it, the data set, if it includes a record of 2020, 2021, it may have that abrupt changes when compared to the previous years. For instance, if you have a 10 decades from 2010 to 2011 to 2021, there may be some changes in the data. And if you look at what happened in Nigeria recently, a change of old note to new note, it has affected a lot of small and medium scale businesses. So if you look at the sales of both formal and informal businesses, there must be some abrupt changes. If you get the data set, you may easily notice that. So now let us look at this. Let me share the screen. Let us take a look at this simple time series forecasting using ARIMA model. Can you see my BS code? Dr. Shamsu?
No.
Okay. Okay, let me share it again. Can you see my BS code now?
Yes.
Yes. Okay. So now using our data set of carbon dioxide. So now let us use this data set to make a time series forecasting. So now, first of all, let us start with important our libraries. As you all know, we have to import pandas, NumPy, matplotlib, and an ARIMA model, which is not familiar with, but for the remaining three, you are familiar with these three libraries. So from startmodel.tsa.arima.model import ARIMA, which is that is ARIMA model. So we are importing ARIMA from this start models library. So in the above section, we import necessary libraries, pandas for data manipulation, NumPy for numerical operations, matplotlib for plotting, and ARIMA from start models for ARIMA model. So now let's start. So now we are creating a data frame from our data set. So now if you look at this data set, it has 4 columns: carbon dioxide, year and month, that is CO2, year and month, year, separate column, and month in another separate column. So now, as I have said earlier, when we are dealing with time series forecasting, sometimes I use these print.columns to call my columns, because sometimes some columns may have a space, added space. So if you didn't print your column, sometimes you may get some issue while trying to set your index. So that is why I print columns, so that I can call it as it is. in my data frame. So now in time series forecasting, as I've said earlier, we don't need date, year, months, or date and time, but they are part because our data is in that pattern using timestamp, using timestamp or date timestamp. So we need that to be our index. If you look at our data frame, initially we are using numbers from 1 to 160 as our index. So now we don't want that. We want our date, time, or date. In our own case, in this regard, we have year, month, year, and months. I want them to be our index. So now df.set index year, month, and inflates true. If inflates true, so now if we look at it, now we have only one column, CO2. So now let's extract the data, which is in this case, the relevant column. In this case, the relevant column from our data frame is CO2. So now we have extracted this. If you like, we can now CO2 data, we can display it. You can see. Oh, CO2 data, CO2 data. So now CO2. So now we are now extracting CO2. So now we want to split our data set into train and test sets. So now in this case, I want 80% of my data set to be for training and 20% for test. So now the next is use of sliding window. As I've said earlier, in time series forecasting, we are using look back or sliding window. We are using look back or sliding window. So sliding window is a technique used in data processing and analysis where a fixed size window moves over a sequence of data points. This window acts as a frame that captures a subset of the data at a given time, and it slides or moves one step at a time, sequentially processing the data. So it moves one step at a time. As I have mentioned earlier, in this case, I want to use window size 2. So this means that in the first iteration of my time series forecasting, it will take 1 and 2 and predict the next one. So in the second iteration, it will now take number 2 and number 3 and predict the future value. And in the third iteration, it will now take number 3 data point and number 4 and make a prediction. In each time, because in this case, my window size is 2. If my window size is 3, it will now start from 1, 2, 3. If my window size or look back is 3, it will now track 1, 2, 3. If it takes 1, 2, 3, it will make a prediction. Then in the next iteration, it will now take 2, 3, and 4. Make a forecasting. In the next one, it will now take 3, 4, and 5 in this order. As the window moves, it maintains a certain width or length, typically defined by a specified number of data points. The sliding window allows for examination of local patterns and relationships within the data. It is commonly used in time series analysis, signal processing, machine learning tasks such as feature extraction or creating training samples. So by sliding window over data, it enables the analysis of different segments and facilitates the extraction of relevant information and patterns in sequential manner. So looking at this, we have now defined our window size as to which is adjustable. If you like, we can change, if we like, we can change it to 3, 4, 5. But there is one thing, as the number of sliding window increases, the computation time will also increases, because now it is 2, so the computation time will be very small. But if you have like 20, 30, so the computation time will be increased, more especially if you are using hyperparameter optimization techniques. It will take some hours for you to make focus if you have like Windows slide of 20, 24, etc. So sometimes if you are using hyperparameter tuning optimization, it will take some hours for you to finish a single experiment. So now, in this, so now, normally in time series forecasting or even in prediction, normally we are making predictions and try to compare our predicted values and actual values. Normally in either prediction or time series forecasting, what we are trying to, at the end of the day, we'll try to compare the predicted values with the actual values. So now I created two empty lists, which is prediction and actual values. So now this is where in this loop, we are trying to train our model using ARIMA model. So in this loop, we iterate through the test data. For each iteration, we define a training window using train data and current window size. We then create an ARIMA model with an order of 100 and fit the training window. We also fit the training window that we create. Then we obtain a one-step forecast using model fit.forecast. We store the predicted value and append it to the prediction list. So if you look at this, this is a for loop. Initially, for a range of length test data, we already split our data set into test and trend set. So now for a range of length, normally we are using this to find the length of data or the length of data set. So length test data minus window size plus 1. So from this is the length of our data set. Window size plus 1. So train window is equal to train data I, which will now be searched within this I plus window size. So ARIMA model train window order is 100. So model.fit is equal is equal to model.fit. Forecast model is equal to model.fit.forecast. We are calling this forecast model.fit forecast. You can call model.fit forecast step 1. We are using this. If you are using ARIMA model, you can call this from model. You can call this forecast from model.fit. So predicted value is equal to forecast.ilog. And I know you have discussed a lot about how to split your data. So we now take it from 0, forecast.ilog at 0. So through that, we can access the forecasted value. So at this, now we are appending our predicted values and actual values to the two empty lists. we have initially created. So now let us run. So while I was running this code, I found some issues. So I have to use if condition because it is giving me some out of bound error. So I have to use some if conditions. So the condition, if I plus window side, I use it this way. The condition if I plus window size is less than the length of test data, ensure that there is enough remaining data in the test data to append to the training data. Because initially, while I was running this code, I was having some issues. So I have to find a way to resolve that issue. So at the end of the day, I have to use this if condition, because it is giving me out of bounds error. So if the condition is satisfied, the next actual value from the test data is appended to the training using the append function. So the ilog I plus window size expression retrieves the value at the index I plus window size from our test data. So at this juncture, I have now created a series. Initially, we are using data source. So now I try to create a series to store our data. So the PD.series is used to create a new series of objects from the value obtained from the test data. That is this. This is a series. The parameter assigned to the corresponding value from the test data to the newly created series object. This ensures that the index values are preserved when appending the series to the training data. So by appending the next actual value to the training data, the model is updated and trained on an expanding data set as more actual values become available from the data set. Our aim is to try to compare the actual values with the predicted values. This is what we are trying to. We are trying to compare the actual values with the predicted values. So now we have now trained our ARIMA model and make an update by appending the values, by appending the actual values to the actual values list, and predicted values to the prediction list, which are the two. So now what next? So now we have trained our model. Now let's try to use evaluation metrics to see or to capture the errors we have during the training. In case of regression problems, the less error you have, the more accurate your model or the perfect your model is. So now, mostly in time series prediction forecasting, like in case of regression, is the same in case of regression problems. Normally, the most commonly used evaluation metrics are mean squared error, mean absolute error, root mean squared error, and R squared. So these are the most commonly used evaluation metrics in time series forecasting. So now I have used all these four to evaluate the performance of our model, to see the error of our model after the training. Now let's so looking at this, okay, I have run it. Oh, I have run it twice, sorry. So looking at this, the first one, if you look at the mean squared error, we have 260.3216 approximately. For the mean absolute error, we have 15.81. Root mean squared error, we have 16.134 approximately. And in case of R squared, we have minus 46.01. Even from this, you can understand that our model is not performing very well. So our model is not performing very well. So now let us look at this evaluation matrix briefly before we see the plot of actual versus predicted values. So, but from this, you can see that our model is not performing very well because the mean squared error is supposed to be in decimal place or floating point value. In decimal place, maybe 0.5, sometimes 0.00 if our model performs very well. So the above metrics are commonly used to evaluate the performance of regression model. Here are the explanation of each. Let us look at this briefly. We are running out of time. Mean squared error. Mean squared error, that is MSE, measures the average squared difference between the predicted values and the actual values. It gives higher weight to large errors. A lower MSE value indicates better model performance. In this case, the MSE is 260.3267. So which means that on average, if you look at this, you can see that the error is very high, which is 260. Now let us look at mean absolute error. Mean absolute error, MAE, measures the average absolute difference between the predicted values and the actual values. It gives equal weight to all errors, regardless of their magnitude. A lower MAE value indicates better model performance. In this case, is 15, still not good because 15 is very high. We want to have an error sometimes 0.00, sometimes even 0.00, because I work with some models where I am getting 0.003, something like that. So which is very good. So root mean squared error. Root mean squared error, root mean squared error, or RMSE, is the square root of the MSE and provides measure of the average magnitude of errors. In the sum unit as the target variable in the sum unit as the target variable, like MSE, a lower RMSE value indicates better model performance. If you look at this, our root mean squared error is 16, which is still very high. Now the last one is R squared or R score. R squared is a statistical measure that represents the proportion of variance in the dependent variable or target variable, that can be explained by the independent variable. In this case, some part of our data set is dependent variable while some part of it is independent, because we are using sliding window. So by the time we are using sliding window, we have this part for test and we have this for training. So it means that both in the same case is the same as dependent and independent variable, unlike in other regression problem where you have features and target separately. Features are the independent variable, while the target is the dependent variable. So this matrix normally help us to assess the accuracy and performance of our regression problem. So this metric will really help you to assess the accuracy and performance of your regression problem. It is important to interpret them in the context of your specific problem. Sometimes in some problems, you may need only one. You may just use mean squared error is okay for you. You don't need more. Or in some problems, you may need to use two evaluation metrics like mean squared error and mean absolute error to measure the errors. Or sometimes you may use root mean squared error with mean absolute error, depending on the type of problems you have. Now let us plot our actual versus predicted values to see whether our model perform well or not. Although we can conclude that from the errors we get, we can conclude that our model didn't perform very well. So if you look at this, between actual and predicted, the values, there is a big margin between the actual and predicted values. So now, how are we going to solve this issue? Because as I've said earlier, normally time series forecasting data, sometimes it is very complex. It has some issues like issue of seasonality, issue of trends, and what have you normally, or outliers, they normally affect a time series forecasting data, which sometimes it will be very difficult for you to handle. At some point, you may need some optimization or hyperparameter tuning and optimization so that you can now tune your model. Either you can tune your model manually, you can use some manual time series forecasting, hyperparameter optimization techniques to tune your model manually, or you can use some available libraries we have like grid search CB, randomized search CB, keras tuning, bias search CB. You can use hyperparameter optimization and cross validation, which will improve the performance of your model. So this is the end of my today's lecture. Now, the question and answer session. Let me check. It's like there are some that ask some questions. Let me check. So the first question is it MD Kabila? The index is already set to the 3 columns. That is the reason why they are here. Yeah, since in this case, our data set, we have carbon dioxide, and the remaining 3 columns are year and month. We don't need them. They have no impact on our data, but they are used as an index so that our model can understand the pattern that this is a time series data. So is from Farida Yusuf, is window size and horizon same thing? In case of we can use window size and horizons, they are two different. In case of window size, the look back, if you are using, you can use window size in either the case. In case of window size, you are just indicating that, let me use this. So there is another technique, which is horizon. In case of horizon, if you take 3, it will now 3 at a time and predict the next 3 values and take another 3 in that regard. But in this case, we use 2. We use 2 as our size of window size. It means that it will now take, if in our data set we have 1,000 data points, it will start from 1 to make the next prediction. It will now take from 2 and 3, make forecasting. It will now move to 3 and 4 because we are using ARIMA model. The ARIMA model is auto-regressive moving average, ARIMA model. So do you have any other question? Dr. Shamsu?
Yeah, Dr. Energy.
So if there are any other, I'm just a student, I'm still learning. I'm still learning from so pardon me if I make some mistake. I'm just a student also. I'm just a student like you. So pardon me if I make any mistake.
Go on.
Okay, so do you have any other question?
Gashi na jana tambaya more on sliding window.
So on sliding window, as I've said earlier, sliding window is like a look back. Maybe let me show you, or maybe you can understand. For instance, now in our sliding window, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So this is from our data set. If you have like 2 as you are sliding, in this case, we have 2 as our sliding window. In the first iteration, our model will take 1, 2. So it will now make the prediction. For instance, it will now make a prediction. In the second, it will now take 2 and 3, make a prediction. In the next one, it will now take 3, 4, make a prediction. In the next one, it will take 4, 5. It will now make a prediction. In the next one, it will take 5, 6. So in this order, did you get it now? This is how sliding window, we call it sliding window or look back. We call it a sliding window or look back. We call it a sliding window or look back. So do you have any other question regarding that? Yes, a question from Dr. Idris. Why do we set index? Can't we just select the column we want to work with? That is one thing. Normally in time series data, mostly our focus is more on temporal feature of the data. Normally, there are some machine learning algorithms that are good when dealing with spatial data, because in case of there are two things, just like space and time. Like in mathematics, we can discretize it, space, time. So the same thing in machine learning, we have to consider temporal dynamic of the data, which is spatial temporal features of the data set. So in time series forecasting, our main focus is more on temporal feature of the data, while in some other cases, our main aim will be more on spatial features of the data. Even in time series forecasting, let me explain more. Even in time series forecasting, most of the times, you will find out that like advanced time series forecasting models like LSTM, GRU, they are still more capturing the temporal features of data when compared with machine learning. So a data set that have more spatial issues, it is a time series data, but it has more spatial issues, that is space. So you realize that when you applied machine learning, it happens to me. When you applied machine learning models, they will perform much better. But in case of temporal, you realize that those advanced time series techniques may not work for you. So the reason why we are using, we can't just use those data as a column. We have to indicate that now our date time or time step is our index. Unlike the way we have in our sequential data, we are using 1 to infinity as our index. So we can't just use that, because automatically our data frame will now consider 1 to 0 to any number as the sequence or the index of our data, which has become a sequential data, not time series data. I hope Dr. Idris understand my point, because if we just use index, it will now become a sequential data instead of time series data. So do you have any other question? Is there any other question?
We are good.
So from this, we can see that we need to improve. Maybe we have to apply some hyperparameter tuning and cross-validation technique to improve our model. In our today's class, we will look at SBM. How can we use support vector machine in time series forecasting? And I will try to also discuss about this again, by trying to improve this model, ARIMA model, using hyperparameter tuning and cross-validation technique.
Yeah, so thank you, Dr. Zaharaddeen. We are already 1 hour on top of our session. Can we continue tomorrow or?
Yeah, because we have just introduced ARIMA model.
Okay.
We have to, tomorrow
Okay.
we'll continue with SBM, and I will try to improve this model.
Okay, cool.
Because
So
that is the reason is that we want the reason behind this is that as me too, I'm also a student. So as a new student to the time series forecasting model, they need to see how time series data behave. You can't just use, sometimes you can't just use time series data as it is and expect a good forecasting result from it.
okay, thank you very much.
Okay.
Thank you very much, Zaharaddeen, and for all those that join us today. Thank you for joining us. We don't want to take much of your time.
So maybe after tomorrow, I will share the notebooks
Okay.
I will
Okay.
share after tomorrow. I will share the notebooks with the students.
Okay. Yeah. So we have a GitHub repository where we push
Okay,
the.
I will drop it there. I will drop it there.
Okay.
So that
Okay.
you can just download from there.
Okay. Thank you very much. For all
Thank you
those
for
that
having me.
joined. Thank you for joining. Tomorrow we will meet the same time to finish the time series stuff, and see you tomorrow, inshallah.
Okay, so thank you.
Okay. So bye bye all. See you tomorrow.
Okay, so.